So in our series of video lectures, so that is in our course 15 Easy 404, we are supposed to see about the processors and then the microcontrollers. So till now we have seen about two types of process. One is 8085 8-bit processor, another one is 8086 16-bit processor. So and then we have seen about the peripherals that we can interface with these kinds of microprocessors. So from today onwards we are going to see about the microcontrollers. Okay, so in the first introduction video lecture itself I have told you about the processor and controller. Okay, so first in processor, so what do we have? We have our processing unit. Okay, processor as a center part. So with this you have interfaced the peripheral devices, analog to digital converter. So and then 8255, then 8237, then memory. Okay, so memory we have used to store data as well as the program. Fine. So and then what else we have interfaced? Then other peripheral devices also, the DMA controller. All those devices we have interfaced with the microprocessor. Fine. The processing unit is separate and then the peripheral devices is also separate ICs that we have interfaced with the microprocessor. So but in case of microcontroller, the whole thing is known as microcontroller. So you have your processor, which is nothing but the processing unit. Fine. And then you have your memory inside the controller, analog to digital converter. Okay, there is no need for 8237 here. DMA is also not there in microcontroller. Then what else? Your I2C for serial communication purposes, SPI, serial peripheral interface. So these two devices we will use for communication purposes. Okay, so such kind of peripherals can be inside the microcontroller. So whereas in the processor we do have a separate IC for analog to digital converter and memory as in separate IC that we will interface with the processor externally. So when you see for microcontroller, you have your processing unit inside and then all the peripheral devices, memory, analog to digital converter, then the device that we use for communication resides inside the single IC. This is a single IC actually. Okay, so these kinds of peripheral devices are residing inside the controller. Okay, so now can you tell me which is advantageous, whether the processor or controller? So obviously processor is advantageous than the controller. So why? In the sense, when you see, as I have already told you, when you see in the processor you are supposed to interface the memory IC externally with the processor. Fine, in that case you can connect the more number of memories. Okay, that is that the processor is capable to address. Fine, so more number of memories you can interface with the more capacity. I am saying you can interface with the processor that the processor is capable of addressing. Fine, but in case of microcontroller, the memory is residing inside the IC itself in case of microcontroller, which means that the memory capacity is fixed in case of microcontroller. So if you are designing a microcontroller with 512 KB of RAM memory, then you will be able to use only that capacity of memory, 512 KB only you will be able to use. Okay, so which means that you are constrained with memory in microcontroller. So that's why the processor is more advantageous than the controller. Okay, processor we will use for more applications, more generalized applications, but when you see a microcontroller we will be able to use only for the specific applications. Okay, so with memory constraints we will be able to use microcontrollers. So that's a small introduction for microcontroller. So the way it is advantageous than the processor is that here we have all the inbuilt peripheral devices, but in case of microprocessor you are supposed to interface those peripheral devices with the processor. So that's the advantage of controller than the processor. So in your syllabus, in this video of in this series of video lectures, we are going to see about PIC microcontroller. So which is nothing but peripheral interface controller. Okay, we are going to see in specific about PIC. So we do have other controllers, 8051, then controller, we do have such kind, but in specific we are going to see about PIC microcontroller. Okay, so we are going to see about the addressing modes, instruction set, general features of PIC, and then the timers, counters. So how the timers can be used, how a PWM output can be generated using those timers. We are going to see that. Fine. So, and I forgot to say you one thing. The peripheral devices that are inside the controller are analog to digital converter, your memory, and then the timer unit is also there inside the microcontroller. That is more advantage. Okay, where in processor we will interface that externally. Here we have internally we have the timer units. Okay, we are going to see that shortly. Fine. So as I have told you, PIC is peripheral interface controller. So this IC was manufactured by Microchip Technology. So this is what the company designed the PIC IC. Okay, so as you see, the 8085, 8086 are the ICs designed by the Intel company. Okay, as of that, PIC is designed by the Microchip Technology. Fine. So this is an 8-bit microcontroller, which means that its data bus is of 8-bit. It is capable of accessing a data of 8-bit only. Okay, so next we will see the features of PIC microcontroller. First we will see, first feature is that speed. So this microcontroller is capable of executing 5 instructions per second. Okay, which means that each instruction will take 0.2 microseconds. Okay, fine. So per second it's capable of executing 5 instructions. So it is speeder than the other controllers, and the architecture that it follows is hardware architecture. We will see that shortly. Okay, so the next feature is that instruction set simplicity. So here we have only 35 instructions. Okay, so to perform all the operations that we want to. Okay, so it has only 35 instructions. So when you compare with 85 and 86, we have in 85 76 and 86 more than 76 instructions are there to perform an operations. Here we have just only 35 instructions. Okay, so that's why this PIC will fall under this sector, RISC sector. What is RISC in the sense? Reduced instruction set computer. So this is a type of categorizing the processor and controller. We have two categories like this. One is complex instruction set computer, another one is reduced instruction set computers. So in reduced instruction set computers, we do have small number of, that means limited number of instructions. Using that we will perform the operations. Okay, fine. And the next feature is that power on reset, POR. So what is power on? This is the most important feature of PIC. So what is power on reset in the sense, when you switch on the power to this IC, which means that when you give supply to the IC at the initial time, what it will do is the registers inside the PIC microcontroller. In architecture we used to discuss now with 85 and 86, we do have instruction pointer, source index, destination index, general purpose registers, special purpose registers. So like this, here also we have all those general purpose, specific purpose, then control registers also we used to have. So all these registers will get resetted to the value, initial value that we have defined. Okay, fine. So the initial value might be FF or 00, it might be whatever we have designed. So it will be resetted to the initial value. So at what it will get, at what time it will get reinitialized? So when you apply power to it. So that condition is called as power on reset. Fine. So and the next important feature is that brownout reset. So what is brownout reset in the sense? So this PIC microcontroller will have a specific range of supply to be given. So for example, say for 5 volt DC, in the sense you are supposed to apply 5 volt. So if it goes beyond 5 volt, your processor will go into malfunctions. To avoid that, this controller will have a feature of brownout reset. It will continuously monitor the power supply that is given to this controller. If it goes beyond the given supply means it will automatically get resetted. So that feature is called as brownout reset. Okay. So when the power supply goes below, for example, we have given 4 volt. So when the supply goes below the specific power supply, okay, so here I have taken an example of 4 volt. If your supply goes below the 4 volt to 3 volt or 2.5 volt, your processor will automatically get resetted to avoid malfunctions of your controller. Fine. So to avoid malfunctions, we are using this brownout reset. So power on reset, brownout reset. Another important is watchdog timer, that we will discuss it now. So these 3 features are most important in PIC microcontroller. Fine. So next feature is watchdog timer. So what it will do is it will reset the processor if the program or software is malfunctions. Okay, which means that when it deviates from the normal operation, it means that your controller is malfunctioning. If it senses your controller is malfunctioning, it will reset your controller. Okay. So how this watchdog timer works in the sense, as I have already told you, inside the controller you have your timer unit. Okay. So initially we will give the values for the timer unit. For example, so if this is your timer register, okay, and you are giving a value of 0.5, okay. So what will happen is, initially we will initialize this timer value with 0.5. So if your processor, if your controller is functioning normally, this value will be decremented to 0.4, then 0.3, then 0.2, then 0.1. So from 0.1 is supposed to decrement to 0.0. When your controller is functioning correctly, it won't allow the timer value to become 0.0. What it will do is, once it has to decrement from 1 to 0, again it will reload the value with 5. So again this will decrement from 5 to 1, from 1 to 5. So this is how will happen at the time of normal operation. Your controller is supposed to auto reload this timer value with the initialized value. Fine. If this is not happen, if this reload is not happen, this 1 will become 0.0, right? Okay. So which means that your controller is malfunctioning, some error has been occurred. So this will indicate that your controller is performing a malfunctioning. So at that time the whole controller will get resetted because of this watchdog timer. Okay, it's watching whether your controller is functioning properly or not. Okay, can you able to understand? So I will tell it once again. So how the watchdog timer works? It works means it will have a timer register separately. You are supposed to initialize it. So when your controller is performing in normal operation without any deviations, so this timer value will be decremented 1 by 1. So when it reaches the last count is 0, 1, okay, whatever value we have initialized with, so it will reach 0, 1 at last. So from 0, 1 it's supposed to decrement to 0, 0. So if your controller is functioning normally, it won't allow to decrement to 0, 0. So it will be again reloaded. The 0, 1 will again become the value what we have initialized at the first. Okay, here I have taken an example 0.5. So from 0.1 it will be increment to 0.5. So this will happen only when your controller is performing normally. Fine. So for example, if your controller is deviates from its normal operation, what will happen now? So this 0.1 will not be reinitialized to the initial value. So it will be decremented to 0.0. So at that time, so the watchdog timer knows that your processor has deviated from its normal function. So it will automatically reset your controller. Okay. So this is how watchdog timer will work. Another thing is, you have your programmable timers and on-chip ADC. Okay, I have already told you. So then here you are having 12 independent interrupt sources. So where we get these interrupts are from hardware, we will get from the peripheral devices we will get. Okay, so peripheral device in the sense I have told you timers, your analog to digital converter. So based on the channels the interrupts are there, and then based on the timers also we will have, if you have 3 timers, so 3 different interrupts we will have. Okay, so and then by I2C and then from SPI, so like this we will have the interrupts. So we have 12 such interrupts sources in PIC microcontroller, and we have our EEPROM. EEPROM is nothing but erasable programmable read only memory. So then OTP, which is nothing but one time programmable, one time programmable, so that is for OTP. Then we have our flash memory. These kind of memory operations are there in PIC. And next thing is IO port expansion capability. So here in PIC microcontroller we will have the pin, we used to call those pins as ports. Okay, 8 pin will constitute a port. Okay, so we do have in general we do have 5 kinds of ports. Okay, so from through this ports we will connect our input and output devices to this PIC microcontroller. Fine. So and the last feature is that we do have a free assembler and simulator provided by the microchip. Okay, so using this PIC you can program it by assembly language, or else by embedded C you can program it. So in order to simulate and compile the programs, you are supposed to have an assembler and simulator. So this microchip company is providing the data sheets of the PIC microcontroller and the assembler simulator as a free one. Okay, you can download all these things from the net and you can use it. Okay, so next we will see about the CPU architecture. So before we will discuss about CPU architecture, I would like to say you that, so as I have told you, PIC microcontroller is having an n number of families. We do have PIC C family, PIC 16F family, 17F family, 18F family, 16C family. Such kinds of series of ICs has been manufactured by this microchip company as a controllers. Okay, depending on the application you can use either of these ICs for your application. So we are not going to see any in particular ICs in our video lecture series of video lectures. Okay, so we are going to discuss in general about the PIC microcontroller. Fine. So in specific, as of in 85 and 86 we are not going to take any particular IC, and we are going to see about the architecture, addressing mode and all, not like that. Okay, so we are in general we are going to discuss about the architecture of PIC, addressing modes, and then register file structures, and then the memory organizations of this PIC microcontroller. Okay, so first we will see about the CPU architecture. So I have already told you this architecture belongs to hardware architecture. So in the introduction video lecture itself I have told you what is hardware architecture. We do have separate memory for data and program to store these data and the instructions in the memory. Okay, so and we do have a separate address to access this data and the program from the memory, so that this would act faster. Okay, the ICs that follow this architecture would act faster, to perform faster, to execute the programs. Fine. So as of that you have your processing unit here, you have your program memory where you will store your instructions or program, and you have your data memory, so where you will store your data. Okay, so this data memory is RAM memory and this is ROM memory actually. Fine. Okay, so we have our separate address lines and data lines, then we have data address lines and data lines. So here the address lines are called as register address. So I will tell you why this register address are used later in lectures, I will tell you. Okay, fine. So then we have your address bus, so sorry, data bus, which is of 8-bit. So since it's an 8-bit processor, and then the program address is of 13 bit, okay, your PC value, fine. So which is of 13 bit, okay. So I have told you already, we have your program memory and data memory separately to store the instructions and data separately to access it faster for the speed execution of our program, fine. So next we will see about pipelining. So pipelining is a basic concept that we are supposed to see in all the process and controllers. So pipelining is used for the faster execution of the program. So pipelining, in the sense, the parallel execution of an instruction is called as pipelining, fine. So parallel execution, in the sense, I have already told you, each and every instruction is supposed to pass through 3 stages of its execution, okay. So this we have discussed. So one is fetch, another one is decode, another one is execute. So here in PIC microcontroller, we just have 2 stages of, in general I am saying 2 stages of execution. One is fetch, another one is decode, okay. So what pipelining concept is, when first instruction will be fetched at particular time and it will be executed in the, it will go to decode in the second set of time, right. So at the time of pipelining, what it will do is, when your first instruction is decoding, at the same time your second instruction will be fetched, okay. So then at the next time your second instruction will perform decoding stage, at the same time your third instruction will be fetched. So this is how the pipelining will work. So by doing so, this will help in the faster execution of the program. So this will reduce the execution time, so that the processor or controller will act more faster, fine. So we will discuss such kind of pipelining now, fine. So this is the time period scaling, fine. So for example, if we take a normal execution, you will have some line 1 at the address 5000, okay. Then at 5001 you are having your second instruction, then at 5002 you have your second instruction. So this is for example I am saying, fine. So at the first cycle, this L1 instruction will be fetched, okay. Then this will be executed at the cycle 2, okay. So I have already told you this is the time period, okay. So at first time period, this L1 instruction will be fetched. At second time period, this L1 instruction will be executed. So decoding execution will happen at the same time, okay. At the same second cycle itself, you can see here, at the same second cycle itself, your second line, okay, this one in the address 5001 will be fetched here, okay. So now you can see here in the same cycle, okay, execution of first line and then fetching of second line is happening. So at the third cycle, your second line is executed here, at the same cycle your third line is fetched here, okay. So at the fourth cycle, third line is executed, at the same time your fourth line is fetched here. So this will reduce the execution, time. So this will help in the faster execution of the program. You could see here, at the same time period, 2 instructions operation has been performed. First instruction is executing and second instruction is fetched. So at third cycle, so this will have second line will be executed and third line will be fetched. This is how. So if this pipelining is not, so when you see here, okay, how many cycles taking to execute 3 instructions, it's taking 4 time period, okay. So assume that this pipelining is not used, then to execute this 3 lines you will require 4 time period, right. So see, where is 4 and where is 6? So now the execution time has been reduced when we use pipelining, okay. So this concept is for there when you perform successive address execution, okay. So for example, see that if your second line is jump instruction, which means that go to some address of 5600, okay. Assume that the second line is go to 5600. So what your controller is supposed to do, it has to execute it So when it comes to this address location, it will cease to go to, then it not supposed to execute the third line, it's supposed to jump to 5600, then it has to execute this line. Okay, that is the process that should happen, right? So we will see how the pipelining will do for this kind of instruction, for go to or jump kind of instructions. Okay, so at the first cycle, as of that, your L1 instruction 1 will be fetched. At the second cycle, the L1 instruction will be executed. Okay, so at the same time of the second cycle, your L2 line will be fetched. So during fetch operation, okay, it knows that the instruction given is go to instruction. So at the second cycle, so what the go to will do is, it's supposed to jump on to the address 5600. Okay, so as we know, the program counter will have the next executable instructions address. Fine. Okay, so when it's fetching this L2 instruction, PC will have 5002, right, during the fetching of L2 instruction. Okay, so now your controller is supposed to jump to 5600. So your PC value is supposed to change from 5002 to 5600. So that's what will happen in the third cycle. So in the third cycle, your PC value will be changed to the new address, which is nothing but 5600. Okay, at the same cycle, your L3 instruction will be fetched. Yes, so because consecutively the operations are happening, no. So what will happen at the same time of changing the address from 5002 to 5600, the fetching of the line L3 will happen. Okay, so now the processor is not supposed to execute this L3 at the second cycle, it's supposed to jump to 5600. So at this cycle, your L3 instruction will be ignored. Okay, so and once it has been ignored, it will jump to the address 5600 and that instruction, L9 instruction, will be fetched. Okay, so can you all able to get this concept? So when it's seeing to the go to instruction, if that instruction is fetched at the second cycle, the address of the PC has been changed. Okay, so at that time the next instruction would have been fetched. So that fetched instruction will be ignored at the second cycle, and then the new address instruction will be fetched at the same cycle. So this is what the pipelining concept. So next we will see about the program memory considerations. Okay, so with the PIC microcontroller, you can interface with the PIC microcontroller. We have a memory capacity of 2 KB, 4 KB or 8 KB. So based on this, the program counter register bits will be determined. Fine. So when for the family of PIC 16C6, okay, we do have either 2K or 4K of memory. So if 2K of memory has been used, we are in need of 11 bits of program counter, and with 4K of memory, we are supposed to need 12 bits of program counter. So when we have 18 KB of memory, your program counter should be of 8K. So why this, how this 12, 11, 12, 13 are determined in the sense, as I have already told you, 2 per address bus will give you the memory capacity. So we know the memory capacity, okay, we are supposed to know the address bus values. So if it is 2K, which is nothing but 2048, so what will give you 2048? 2 per 11 will give you 2048. So that is how we have determined this. Okay, so for 2K of memory, your program counter with this 11 bit, for 4K it's 12 bit, for 8K it is 13 bit. Fine. So up to 8K of memory, it can be used with PIC microcontroller. Fine. So now we will see how this program counter can be used for addressing the memory. Okay, so first thing is for 2K of memory. Okay, so 2K of memory will be from 0000 to 7FF, right? So this is the most last address, this is the first address. Fine. So for 2K of memory, I have already told you 11 bit of program counter can be used. So this is your program counter register. From 0 to 10 bits only will be used. So 11th and the 12th bit can be ignored. Okay, so whatever values can be inside this, it cannot be utilized here. From 0 to 10 it is used. Okay, so for 4K of memory, so the address will be from 000 to FFF. Fine. So here we are supposed to use 12 bits of memory. From 0 to 11 we can use it. The 12th bit is ignored here. So from this value you can point out to a specific address. So when you see here, so we are framing an address 3A5. So when program counter is values 3A5, it will see to the memory to a specific location 3A5. From that it will take the instruction and execute it. So like that also here. So the 11 bits of program counter will frame an address location. Okay, so the processor will see to this program counter, frame the address, look into the memory and execute the instruction in that memory location. Fine. Okay, so I have already told you that based on the situations your controller will get resetted. So what will happen when it get resetted in the sense, so your program counter will be reinitialized to the value 000. Okay, so what your controller will do is it will go to the memory. So consider this as your memory. Okay, so to the location 00, because your PC has been reinitialized to the value 00, it will go to this address. Okay, so where the mainline program, mainline is nothing but your application program. So your application program starting address will be residing here. So for example, if your application address is 365, then this 365 would have been written here. So by seeing this 365, your controller will come to this main line and start to execute this program in the mainline range of memory. Fine. Okay, this is what will happen when your controller is resetted. Okay, at reset time this will happen. Okay, so for example, if an interrupt occurs, okay, so what the controller will supposed to do, it has to store all the status of the program into the memory, then it's supposed to jump to the subroutine program to execute the subroutine, particular interrupt subroutine program, right? So this we have seen in 86 itself. So for each and every subroutine we do have its own address locations mentioned in the memory. So likewise here also we do have it. So when an interrupt occurs, your processor will be process program counter will be given with the value of 004. So when the processor is resetted, the program counter is given as 000, no? So likewise when an interrupt occurs, your program counter is given a value of 004. So at 004 memory location we do have interrupts subroutines memory address, starting memory address. By seeing that, it will come to the interrupt subroutine range of address. So from there it will execute the ISR, interrupt subroutine program. So as of here you see the program, a range of address can be used for storing the main program, a range of address can be used to store the interrupt subroutine, and then the starting address for the main line and the interrupt subroutine. So this is how the memory has been segmented and used. So and for storing the tables, okay, so for that also a specific range of memory location has been allocated here. So you can see here, so this range of memory has been allocated only for storing the table values. Fine. Okay, so when your processor is executing, next thing, when your processor is executing a call instruction, it's supposed to address to a range of 2K or 4K of memory. Okay, this has to be determined, no? So for 2K 11 bits can be used, for 4K 12 bits can be used. Okay, the address range of 2K would be from 00 to 7FF. So for 4K it is from 800 to FFF. So this is the address range for 2K and 4K of memory. So to see the difference, we are supposed to use PC latch register. Fine. Okay, so the program counter of 13 bit for 8K of memory. Okay, so in that 0 to 10th bit can be used to address this part. Okay, 2K of memory, which means 11 bits. Okay, so used to this 11 bits are used to address this 2K of memory. from 0 to 11 it is used to address this 4K of memory. Another thing needed to differentiate the 2K and 4K is PC latch third and the fourth bit. Okay, if the third bit is 0, okay, see here, if the third bit is 0, you are accessing the 2K memory. If the third bit of PC latch, okay, if the third bit of PC latch is 1, which means that you are accessing a range of 800 to FFF range. Okay, so these bits are taken from the program counter 0 to 11 bits for 4K of memory. Okay, fine. So on the third bit will define you, that means the 11th bit. So 0 to 10 you can take from program counter, and the 11th bit will decide whether you are accessing from the address range 000 to 7FF or 80 to FFF. So if the 11th bit is 1, in the sense you are accessing this 4K byte range 800 to FFF. So if it is 0, you are accessing this 2K 000 to 7FF kind of memory. Okay, so this 11th bit you will take from third bit of PC latch register. Okay, fine. So that's the concept here. So your PC latch register's third bit will define you whether you are accessing a 2K range of memory or 4K range of memory. Fine. So next we are going to see about the register file structure. So as of 8596, here also we do have two kinds of register. One is general purpose register, another one is special purpose register. So we know it already, the general purpose registers are used to store the data that we are needed for the program. Either it's not specific in purpose, you can store all kinds of data inside the general purpose register. You can use it for all the operations, either it can be arithmetic or for the logical or for data transfer. So all these kinds of operations you can perform when we use general purpose registers. So in case of special purpose register, it is used only for a specific purpose. So as of program counter. So program counter is a specific purpose register where the address of the next instruction to be executed will reside. That's a specific purpose, no? So in general you can't store the operand inside the PC. You'll be able to store only the memory address of an instruction to be executed next, right? So that's those kind of registers are called special purpose register. Okay, so here the location, each and every location of RAM memory is used as general purpose register. Okay, so in PIC what the special case is, here each and every register is named by its address. Okay, so this is a special purpose here in controller. So all the registers can be addressed are used in the instruction by its name also. Okay, so name also you can use it, or by the address. So each and every special, either it can be special or general purpose registers. So everything is given as everything is given with the memory location, memory address. So you can use that memory address in the instruction for its operation. Fine. So as I have told you, the general purpose registers are the RAM memory. Those are special purpose registers are input output ports, and then the control registers. Fine. So this is what your register file structure. So we do have two banks of register. One is bank 0, another one is bank 1. Each of a capacity 128 bytes. Bank 0 is of 128 byte. Bank 1 is also of 128 byte. Okay. So this is addressed from 00 to 7F, and bank 1 is addressed from 80 to FF. Fine. So in this, from 00 to 1F our special purpose register is there. From 20 to 7F your general purpose registers. Here in bank 1, 80 to 9 of special purpose, A0 to BF is your general purpose, and CC to FF is also general purpose. Fine. So this is how your registers are structured. Okay. So the registers I have told you is nothing but your RAM memory. So your RAM memory, each and every location will be given an address location that we have mentioned aside. Fine. So other than your general and special purpose register, we do have CPU registers. Okay. So the CPU registers are working register, status register, FSR, INDF, PC latch and PCL. So we are going to see about all these registers individually in 2 or 3 minutes. So before that we are going to see about the addressing modes of this PIC microcontroller. Okay. So already we have discussed what is addressing mode, what's the purpose of it, and the types of addressing modes in 85 and 86. So we do have different kinds of addressing modes in 85 and 86, but the purpose is same. The way we represent the operand in the instruction is known as addressing modes, right? So in 85 we do have 5 such addressing modes. In 86 we have 12 such addressing modes. So but here in PIC we do have only 2 addressing modes. One is direct, another one is indirect. So you know already what is direct addressing mode and indirect addressing mode. So in direct addressing mode we will mention the operand's address in the instruction itself, right? We do that in direct. In indirect we will mention the address of the operand in the register. So that's the difference between direct and indirect. So if you directly mention the operand's address in instruction, that is direct addressing mode. If you mention the address of the operand using a register, that is called indirect addressing mode. The same concept here is also used. So instead of the operand address, we will mention the register's address. Fine, got it? So previously we have discussed, no, we do have bank 0 and bank 1 of memory for registers. So each and register will have its own address. Okay, so that if you mention the register address directly in the instruction, then it is called as direct addressing mode. So if you mention that register's address using another register, that is called as indirect addressing mode. So that is more simple here. Fine. So in the previous diagram itself, I have showed you each and every register is mentioned by an 8-bit address. Okay, do you remember that? So I will show this once again. Okay, so here we have our registers and the registers are mentioned with the address. So 7F, 20, 21. So all these values are of 8-bit. Okay. So if you mention that 8-bit value in the instruction itself, okay, then it is called as direct addressing mode. Okay. So I will explain you it with the diagram. Okay. So this is your memory, bank 0, bank 1. Its bank 0 address ranges from 00 to 7F. Okay, then bank 1 address is 80 to FF. Okay, the 8-bit 0 to 7-bit will tell you to which it will tell you. So from the program counter, the bit number 0 to 6 will tell you the address, and then the 7th bit, nothing but your 8th bit, will be from RP0 bit of status register. So we will discuss it detailedly in the next 2 minutes. Okay. Okay, so this status registers RP0 bit will define you whether you are accessing this bank 0 or bank 1. So if that value is 0, which means that you are accessing bank 0. Okay, so if that value is 1, which means that you are accessing bank 1. So here I have taken an example here. This is your PC register. From bit number 0 to bit number 6, you have some values which is nothing but 00, 10, 100. Okay, so then this will frame a value 14. So okay, so 4 here. Okay, here you have 1 automatically. So since you have 001, so this bit will define whether you are accessing this range of memory or this range of memory. So now the value is 0 here. Now we have framed the address 14. So which means that you are accessing the address, register's address 14, which is in bank 0. Okay, the same example here, same value 001, 01, 00. So this will frame 4 and this will frame 1 here. So but the RP value 0 is 1. So which has make the value to 4. So 94 is the address value framed now. So 94 belongs to bank 1. So now we look on to the bank 1. Okay, so in direct addressing mode we will mention the address, register's address in the instruction itself, So in that 0th to 6th bit we will take from the program counter, and the 7th bit we will take from the RP0 bit of status register. So that will decide whether we are accessing bank 0 or bank 1. Fine. So and the next addressing mode is indirect addressing mode. I have already told you that if you mention the register's address in another register and that register is mentioned in the instruction, then it is called as indirect addressing mode. So here we are indirectly giving the register's address. Okay. So here in specifically we are supposed to use the register FSR as a pointer register. So where you are supposed to store the register's address. Okay, that is default here in this type of addressing mode in PIC. Fine. So here in this, the 8-bit address of the register is mentioned only in the FSR. Okay. So when your controller knows, how your controller knows that it's an indirect addressing mode, in the sense it will see to the value of INDF register. So if the INDF register value is all the bits of that INDF register is 0, which means that the registered address is indirectly mentioned, which means that we are using indirect addressing mode. Then your controller will automatically look into the FSR register, so takes the value from there, so and that value is your register's address. Fine. So I'll explain you with a diagram. So this is your memory bank. Okay. So this is when your processor see to the INDF register, all these values are 0, which means that the processor has to look into the FSR. So now it will look into the FSR and look to the values. Now the value is 94. Then your processor will go to the location 94, knows whatever the registers and performs the operation what we have mentioned in the instruction. So this is how indirect addressing mode is used. So here in specific we are supposed to use FSR register to store the register's address indirectly. Fine. So now we will discuss about the CPU registers of PIC microcontroller. The first register is working register. So this working register is like accumulator in 85 microprocessor. So in 85 microprocessor, for performing an operation we are supposed to use an accumulator, and the result will be stored in the accumulator. So likewise what will happen here is, so this working register is used as a source of the operand, so and the destination to store the result. This is default here. So one of your operand should be in accumulator and the result will be stored after the operation performed. The result will be stored once again in the working register. Okay. So I have told you this function is similar to the accumulator in 85. Fine. So the next register is status register. So this status register is similar to the flag register that we use in 85 and 86. So there in 85 and 86, the status of your program will be indicated by your flag register. Since the flag register will have the bits like carry, auxiliary carry, sign, overflow, parity, 0. So like that the bits are there in flag register, no, that will tell you the status of your program. So likewise here the status register is of 8-bit, and this in that 8-bit each and every bit is mentioned with some function, and that will give you the status of your program in the microcontroller. Okay, we will see the bits of that status register now. So this status register will be affected after the arithmetic operations or by the transferring of the memory. Okay, so this is an 8-bit status register. This is a status register. So in this, the 0th bit represents the carry or borrow bit. So this will be affected when you have when you are performing an addition or subtraction after 7th bit, which means at 8th bit if you get any carry, this flag will be affected. Fine. And the next is DC, which is nothing but digit carry or digit borrow bit. Okay. So when you have a carry or borrow from lower nimble to the higher nimble. So what is nimble? So 4 bits are called as nimbles. So when you have the carry from lower nimble to higher nimble, this DC bit will be set. So this is similar to the auxiliary carry in 85. Do you remember that? and the next is Z flag, which is nothing but 0 flag. So when your result has become 0, this bit will be set. Okay, and next is PD bar, which is nothing but power down mode. So PD bar, in the sense, this is active low, which is not PD, reset status bit. Okay, when the reset has been occurred by power down, power on reset, a power down mode, so this bit will set. Okay, this is not of TO, which is nothing but timeout bit. So when the timer is out, which means that when the timer is overflowed, this bit will be set. So because of this, the processor, your controller, will be resetted. And next one is RP0, register bank select bit. So this we have seen already when we are seeing this program memory or the bank selection. So if this RP0 bit is 0, we will ask bank 0 registers. When the RP0 bit is 1, we will ask access the bank 1 registers. Fine. So now we'll see about not of PD and not of timeout. So PD is nothing but power down and T0 is nothing but timeout. Okay. So your controller is capable of going into sleep mode by these two things. So when your power is down, it will go to sleep mode, or when the time is out, it will go to the sleep mode. Okay, either of these things will happen. When your controller goes to sleep mode when the time is out, this bit will set. So when your controller will go to sleep mode, PD bit will, because of power down, the PD bit will go low. So by seeing to these bit, your controller will come to a conclusion on what thing it has goes to in sleep mode. Fine. So and the next register is called file select register, which is nothing but FSR. So this FSR we will use as an address pointer where we store the register files address. So this we will use only at the indirect addressing modes. Okay. So that's the purpose of file select register. From the name itself, you can understand that it is used for selecting the files. So file is nothing but registers are called as files here. Fine. So this is used at the time of indirect addressing mode to indirectly representing the address of the register to be accessed. Fine. So and the next register is INDF. So INDF is nothing but indirect through FSR. So this indirect through FSR INDF register is not physical register. So the programmer cannot access this register. That's the meaning for it. Okay, fine. So this register you can use to represent that you are supposed to look into the FSR register at the time of indirect addressing mode. Fine. So the values of INDF will indirectly mention you that you are using indirect addressing mode. Fine. So and the next registers are PCL and PC lathe. So PC lathe is nothing but program counter latch. Fine. So the PCL is nothing but the lower 8 bits of program counter is called as PCL. So if you have your PC register, which registered values from 0 to 13. So from 0 to 7 is nothing but your PCL register. Okay. So on the upper 3 bits of your program counter is PC lathe. So this will remain 0 and serves no purpose there. Okay, fine. So this is your program counter from 0 to 12 bits. Okay. So from this 0 to 7 is nothing but your PCL. So 0 to 4, which is nothing but 8 to 12 is nothing but your PC latch. So that will decide the range of the memory locations that we have seen in the program memory considerations itself. Okay. So in this series of video lecture, we have seen an introduction for microcontroller, then the features of PIC microcontroller, the register file structures, addressing modes, and then the program memory considerations of PIC microcontroller. So in the next video lecture, we will see about the instruction set of PIC microcontroller. So do remember that we didn't see anything in specific PIC microcontroller here. In general, we are discussing it. Fine.